Then, basically the superscalar with dynamic scheduling and with speculation are the best we can do. Now there are a lot of variations in here, and there are things in here which we did not discuss, and they will start playing an important role. Is the instruction fetching. How do I deal with the instruction fetching when I have a very hungry machine which can issue, let's say, each and every cycle, maybe 16 instructions? I have to find 16 victims. To find them, I have to have a large pool for slaughter. Then somehow I'm starting to interfere with the memory system in not a very nice way, because I'm putting pressure on the memory system to give me instructions, and more instructions, and you know, memory system has different kind of things in mind when it's organized, and I'm trying to make the memory system work as nice as possible, and sometimes things are contradictory. Okay, now let us look further at this story. Where is my beautiful remote control? Okay, this is a beautiful table where you have the common name for the multiple issue processor, some examples for them, and how things are done, you know, on issue, detection, scheduling, whatever. I won't go in details on that. You can read from the book. On this one, I kind of already told you that static superscalar and VLIW are very similar, and there are some simple differences. Both rely on compiler, and the main difference is that in a superscalar statically scheduled instructions can jump each other at runtime. Okay. This is an instruction, a machine, you know, an example machine, which I can imagine, and there are machines like that. You see there are 2 instructions per cycle that I can issue, and they are clustered in groups. I can issue 1 integer and 1 floating point instruction at a time. And there is no restriction on the placement on the type of instruction, as I wrote there on the whiteboard with green ink. Then a certain slot, it's associated with a certain type of instruction. In VLIW, this is the rule. Then issue slot 1, it's associated with that type of instruction. Issue slot 2 with that type. Then you split the instruction in classes in order to better deal with the complexity of the process. Now, there are a couple of problems here, and I was mentioning the fetch. And here we have a very simple machine which may suffer from a very nasty situation. You fetch 2 instructions at a time. You fetch the instructions from the instruction cache, where instructions are one after the other, and it may happen that you are not nicely aligned with the cache line. I'm assuming that you know a bit about cache, even though we'll revisit the cache later on, but we have to start from somewhere. I could have started from the memory organization. Most of the people start from the processor organization, then we go with the crowds. Now, in the cache, I'm getting a line, and my first instruction, it's in this line, and the next instruction, it's in the next cache line. Then they are not in the same organization, and then I have a problem to get them from the memory in a fast way. And this can be dealt with by aligning the instructions in the cache, and this can be done also by the compiler. But this is a very, you know, I'm fetching 2 instructions and I'm getting such a problem. Okay? Should I tell you a bit more about the cache? Because I see some faces which are a bit blank. Then a cache is a window on the main memory where I have some kind of copy of what I have in the main memory. And the cache is organized in lines. Then, while for the memory, the basic item is a word, being it 16-bit, 32-bit, 64-bit. For the cache, the basic item is the cache line. And one cache line may have more words. Let's say I have instructions, and somehow my program started here, because that happened. I fetch two instructions, are those there here in the cache line, I see them, I fetch those, again two instructions, that's 1, 2, and then I'm looking for this. But this has a, you know what, a pair, but the pair is not here. And it might not be in the cache, it might be in the main memory. Then if I'm not taking right precautions, I'm trying to get to instructions which will generate a kind of exception in the system, which will induce a lot of penalty. Then I have to be sure that I am doing the right job in the interaction with the memory. Because if this one is, the first one I get, it's in the cache, but this one may require that I'm going from the cache to the main memory, and then I'm doing the transaction between cache and main memory, and that may take millions of cycles. Oh, millions, I'm exaggerating, but it's a long time. Now, because my machine is simple, I have just two classes. I can check the hazards easily. They are their instruction type. And from that point of view, things are simple. Okay. This is a kind of the execution of such a machine. You see, each cycle, I'm issuing, I'm dispatching, I'm executing, I'm going to the memory, whatever. And what you see is that maybe the floating point instruction will create 3 cycles for execution, while the integer instruction is taking one cycle. And maybe sometime, due to some kind of hazard, I cannot do things exactly one after the other. Now, there are a bit more complications in here, which we can deal with. And one of the, let's say, not complication, but one of the things that I have to be aware of is that such a construction is not paying back a lot. The idea will be to be able to issue 2 instructions per cycle. I can do that only in an ideal case, when 50% of the instructions are integer and 50 are floating point, which no way. Then such a machine will not give you the big promise which is making, except if you have certain special applications. Okay. Now let us look at the things with dynamic scheduling. Then Tomasulo, you know, right? If I wake you up in the middle of the night, I call you, you tell me Tomasulo. In my dreams, in my nightmares maybe. Then that instruction scheduling, dynamic instruction scheduling relies on Tomasulo. The only thing that I'm doing is I'm making Tomasulo more powerful by issuing more instructions in a cycle. Now, there is an example here which is good to follow a bit because it's telling us something about what will happen when we assume a certain architecture. This is an architecture where we have a dual issue superscalar. It's dual, but it's dynamic. Then I'm doing dynamic issue. I'm not doing speculation. There is one integer functional unit, a floating point unit, I have a separate functional unit for branch prediction, issue, a writer, one cycle, perfect branch predictions. I don't have forwarding, and this is the latency for each operation. One cycle ALU, 2 cycles for load, 3 cycles for floating point. A friend of mine came with this architecture, and she said, right, that this is a brilliant one. And the question is, how do I know it's brilliant or not? There are two things. I can run benchmarks, then I make an instruction cycle accurate simulator of that processor, and then I run benchmark and I see what the statistics are. But I can also try to do a simple exercise and see where the bottlenecks are. And for that, I can assume a program. This is a beautiful program. You know, I don't care what it's doing, but there are instructions which I will execute by hand now, as there are many examples in the book. And I will see how the instructions will be treated. And this is my table. Then I have a loop, and I have the number of iterations. I have the instructions in each iteration, and I am now following the execution history of the instructions given the constraints that I have for my processor. Then, first cycle, I get, you know, the first instructions, it's a load and an add, and I issue them in parallel at cycle 1. They are okay. I can issue them. But while the load can go further, and I will assume that this will complete at cycle 4, the add has to wait for F0. Then, until F0 is not available, I cannot start the execution of the add, because there is no forwarding. Then the result of the load will have to go in the register file, and only after that will become available to me. Then the add has to wait for the load, and it will take 3 cycles to complete. Then I started in cycle 1 this, and they will evolve in this way in the pipeline. In cycle 2, those instructions will be in different stages, but I get 2 more instructions. Then I have to make a store, and then I'm making an integer calculation. Now, the store, both of them will be issued in cycle 2. The store will begin execution in cycle 3, but it will wait for the addition to complete. Because if the addition is not ready, I cannot start, you know, the memory access. Then after the addition is ready, the result is in the file, in the register file. On cycle 9, I can start the memory access, and I can write there. Now, when I look for the adder, this is an integer add. I'm starting, you know, issue of cycle 2, but I have to wait for the ALU to finish the calculation of the memory address, and then I can start, you know, this at cycle 4, and so forth and so on. Okay. Now, I can look in this table, and you can see how things are done. Then I see now that there are different things which are kind of, you know, precluding me on doing things faster. Then like this one, waiting for the ALU. If I would have a different ALU than 2 of them, I could do things faster. Now, if I just look from the bird eye to the situation, I will say, you know, each loop, which are, you know, 5 instructions, I am actually fetching and issuing 5 instructions each and every 3 clock cycles, which will give me an instruction per cycle of 5/3, which is 167. But is this true? It is not, because I should look at the number of instructions that I can complete. And if I look in this execution, I see that I can complete 10 instructions in 11 cycles. Then my IPC, my real performance, it's under 1 instruction per cycle. So, how can I do better? If I schedule more iterations, I can do better. And this will eventually end up in filling up the reservation stations. I can also do better if I solve some of the hazards. Now, this is an analysis which is like an exercise just for you to see how things are progressing. But in this way, I cannot really qualify an architecture. I can see some weak points, which I can also see if I'm thinking more abstract. But it's like a good exercise. That was one story. Performance was limited because that are kind of conclusions. I had only one ALU, which had to do 2 things: integer calculation and effective address calculation. Remember, I had to wait for the ALU. Normal modern processor have a special ALU to do address calculation. Actually, some of them have even 2. DSP, mostly processors, which are dealing with a lot of data, you know, they are working with matrices. They usually have 2 ALUs for that kind of thing. Now, if I add that thing, then we'll get up in doing slightly better. Now, those are essentially the limiting factors for this machine. Okay, now we've been into this story, and should I say it again? I said it, I think, in the last hour, or not, about speculation. Now the question is how much to speculate. If I don't speculate, I have resources which are idle, right? Then the aggressive attitude will be, you should speculate as much as you can. But speculation is costly, and if something exceptional is happening, things are really detrimental. And what is typically happening is you do speculation as long as you do not create an exception in the system, which is very, very costly. Like, you speculate, and if you go on that direction and you create a miss in the first level cache, you are okay. But if you speculate and you create a miss in the 2-level cache, or in translation look-aside buffer, to some people those are words which are, you know, they mean nothing. They will eventually mean something for you. Those will imply a penalty of tens, maybe 100 cycles. Then if I speculate at such a cost, I better not do it, I better stop it. Then when I start the speculation, I look at what is happening. You know, when I'm not finding the information in level 1 cache, it will come from level 2 in a couple of cycles. 2, 3, depends, 5. But if it's not in the level 2 cache, it may take 100 cycles to bring it, which will nullify all the advantage of the speculation. Then I better stay quiet, wait for the branch to be solved, and see exactly where I want to go. Now, this is very aggressive, and high-performance processors do that prediction and speculation on multiple branches. Now, there are most of the time side effects which, from the conceptual point of view, are not really important, but they limit the performance. due to the fact that you have to do now speculation and you have to issue multiple instructions each cycle, the issue logic is becoming more complex. You have to deal with a larger complexity. And most of the time, in order to solve that, you do pipeline. Then there are a couple of ingredients in the toolbox of the computer architect. One of them being pipeline. Then whenever you have a problem, try to see if you can pipeline it. Pipeline can help you. There are other ingredients as well, but this is one kind of standard. Because you care for throughput, not for latency. And this applies only when your hardware is busy in a continuous way. You know, throughput and latency, they tell me the story of the time delay. Latency relates to the time it takes for the input data to propagate at the end of a circuit for the entire circuit, and the throughput relates to the time it takes for the circuit to create a new output value. And that depends on the delay on the pipeline stage. And maybe I should tell you a bit about that. Then when you split, you know what you do is you have a big piece of meat, which is your hardware, which is doing the job, and you cut it in parts. Now between the parts, you have to put registers to store intermediary data. Now those registers cost also hardware, and they also have a kind of extra delay requirements. It's what we call the hold time and the setup time. Then the throughput will be determined by the delay in the slice plus hold plus setup plus a certain safety margin which you have to consider due to what is called variability. Then pipelining is quite a good means. Now, branch prediction accuracy is getting more important because now you are issuing more instructions in parallel, and if you go wrong, the amount of things that you have to undo, it's actually larger. Okay. Now, in order to deal with this hungry machine, you have to fetch instructions. And you have to fetch a number of instructions per cycle. Now, standard may want to have at least 4 to 8 instructions, but if your issue width is larger, you may have to fetch a lot more. And there are a couple of things which are related to the fetch. And we'll discuss here a bit about how to do the fetch whenever you deal with branches. And those are kind of, constructs for that. Now, when you have a branch and the predictor is saying that the branch is taken, you have to do a calculation because your branch will go to a certain address. Now, if you look in the table, in the branch history table, you assume that that branch was executed before because the history is there, right? It might not be true, but you start with this assumption. If the branch was executed before, it means that you already know the address where you should branch. You already computed, right? Then assuming that no aliasing happens, you can make a buffer where when you solve a branch for the first time and it's taken, and you compute the address of the branch, you store that address. Now this will help me to speed up the execution. Why? Because I have a branch, I know it's a branch, I have the predictor which will tell me what to do, go or not go, and I also have the target address which was computed in a previous cycle. Then I can directly go to the target. being whatever it is. Now, for that, we have something which is exactly like a cache. Then it's a small memory buffer where I'm storing the address of the branch, if it was executed before, and now I'm addressing it with the same bits that I'm addressing the branch predictor, the branch history table, but now I have to be sure that I'm not doing aliasing. Then while these bits will tell me something about the branch, as it is from the point of view of the prediction, I have to be sure that the branch that I'm looking at is the right one. Then in the table, a part of the target, I'm also storing the rest of the bits in the program counter of the branch. Then what is happening is that I'm looking at a program counter and I'm saying, is that a branch? No, it's no branch. Then I execute normally. It is a branch. Is the branch in my buffer, in the target buffer? How do I know that? I take the 3 bits, I address this location, and then I compare whatever is here, this is called the tag of the branch, with the rest of the bits in the program counter. If they fit, we are talking about the same branch. And if we are talking about the same branch, whatever is here, it's the target address. I already have it. And then if the branch is taken, which will tell me from the history, I am ready for execution. And this works quite nice and is saving. First time I have to compute it, but from now on, things are okay. All the things which apply to caches will apply here. Okay, I have to evict when it's full and things like that, but somehow there is a chicken egg story here. And okay, and this is how things are done in the MIPS pipeline. This is the program counter, which is looking in the instruction memory. Okay, and I can have the option of going to the next program counter, or I can have a branch, and when I have the branch, I'm looking in this table. If the branch is in this table and it is taken, then I have already the value here, and I can go further to fetch it. And this can speed up things quite a lot. Now, there are other branches which are related to the return from functions. Then I'm executing a function, and then I'm saying return from the function. This is also a branch, because I've been in the function, I'm ending here, and I'm returning to the address which called the function. Then this is a jump, right? Now, this is something that I can deal with if I create a structure like a stack. Because when you do the execution of functions, what you do is you push the return address in a stack. And then when you return, you take that one from the stack and you go there. I can create that in hardware, and I can do return address prediction. Okay? It will not work all the time, but most of the time, with very limited amount of entries, I can do that prediction as well. And each kind of trick is dealing with different kind of branches. I mean, if I do a branch prediction on such a branch, which is returned from a function, it won't work. Okay. Now, this I kind of told you about the fact that I may have misalignment and things like that. And this is mostly going a bit towards memory hierarchy and caches. I think it will be better if we revisit this a bit later, and when we'll talk about caches, because everybody will follow in a better way. Now, what I would like to do with the fetch is to provide the processor always enough instruction to execute. And there are different techniques of doing that, and people are trying, you know, to improve this interaction between the processor and the memory system. And one of the most effective way is to create a buffer of instructions with what is called prefetch. And you can do that on the control of the program. There are processors which do have prefetch instructions, and they allow you as user to deal with that, or that can happen under the control of the hardware. What this prefetch is doing, it's solving issues which are unpleasant in the communication with the cache, like disalignments and stuff like this. And it's a process which is working decoupled of the rest of the execution to provide instructions, a large number of instructions in a buffer. Now there is another interesting construction which is called trace cache. When you execute a program, what is happening is that you go then you start here, you execute for a while, then you have a branch, you go here, you execute for a while, then maybe you return here, and things like that. You know, this is the layout of the program in the memory. If this is in this way, when you fetch instructions, you know, you fetch here sequential, and then when you arrive here, you have to jump. Then a cache will have a magnifying glass on the memory, which is going in a, like in a rectangular shape sequentially. Then you can move it from here to here, from here to here. Then we'll revisit those. Now, what you can do is while you execute the program, you construct the trace of the execution in a cache. Then instead of taking, let's say, this piece and putting it here in this cache line, what you do is you take the execution of the program and you put them in consecutive location in a cache, which will follow, let's say, this will be consecutive, then will follow this consecutive and this consecutive in your memory. Then your line will not be organized in this way, but it will follow the cache execution trace of the program. Which means that you will have available sequentially instructions which are otherwise not neighbors in your memory system. Again, this is a bit ahead if you don't get the memory organization. Then I should better discuss this when we speak about memory. But this is a nice quick. Okay, now, cool. There are some limitations of these multiple issue processors. I can put as many functional units as I want, ideally. But there are two things. One is that the available instruction level parallelism in programs is limited. And I have to expose a lot of this to the processor. And second, if I have an issue machine and I have to check the hazards, the dependencies between n instructions to provide those n instructions to the output, I will have to deal with a complex problem which is in the O of n squared. Now, if n is 8, it's still doable, but if n is, let's say, 1000, my hardware will explode. And then from that point of view, it's very interesting to try to understand, in the same way we did for branch prediction, what is actually happening when you change different parameters of the machine, like the issue width, the capacity of the renaming register file, the capacity of the reordering buffer, the branch prediction and capacity of the table. Then you have, in principle, an architecture which is generic, and then there are parameters which you can change. And you can change parameters in the sense that you can choose different dimensions for different resources, or you can change parameters from the point of the strategy that you use. What kind of branch prediction I'm using, okay? Now, this exercise, it's usually the exercise that computer architects are doing in order to qualify, you know, different architectures and their potential in practice. Now, again, speaking about the limitation, if I have a very wide issue machine, I should be able to do like register renaming on more registers in one cycle. Here I have an example of 4 instructions. It's a 4 issue where it's fine. I can issue that if I do renaming because there are no real dependencies, which means I start with this and I have to be able to create that where P11 and P23 and 22 are actually not visible registers, but are registers internally, like reservation stations, you know, and registers like that. I can do that easy for one, but I have to do for many. Also remember when we were speaking about Tomasulo, I was saying, you know, if a reservation, it's a functional unit, finishes, puts the result of the broadcasting bus, and then whoever needs the result will take it. Now this is for one. If I have many, I have 2 options. Let them do in a sequential way, then each cycle will be one broadcasting. But if I have such a huge machine and I have more instructions which are processed and executed, I should be able to broadcast also the results in parallel. Then if I'm issuing 4 instructions, I'm executing them also on the common bus. I should have a structure which will allow me to broadcast 4 instructions, which means I will have to have 4 buses, or I will have to imagine something which will allow that. If I'm not doing this, I'm creating a bottleneck. And I want the machine to be nicely balanced, no bottlenecks. Okay. To understand the implication of various choices on a multiple issue superscalar processor, we can do some nice experiments simulation-wise, and as we did for the branch prediction, we start with what is called an ideal processor. This is something which I cannot implement most likely, but I can assume that this exists in the sense of evaluating an upper bound. If I would be able to implement it, what would be the maximum cycles per instruction that I can get, or instructions per cycle, because they are telling me the same story. And here it's an assumption of the ideal processor. I have register renaming with infinite amount of physical registers. Not possible, but I'll assume that. In software, in simulation, if I have enough memory in my system, I can do an allocation of that. I have perfect branch and jump prediction. I always have clear addresses, then there is no aliasing, there is no things which I have to deal with at runtime. All the things of the load stores are known to the memory are not unclear. Then, I'm assuming also something which is completely not true, that each instruction will take one cycle, regardless of what instruction is. And the only thing which I cannot assume different is the true data dependencies, because those are, I cannot get rid of them. Then everything will run on my processor at maximum speed, because whenever resources are needed are there, and things are done in no time, basically, because I said one instruction per cycle. And now the question is, how good can I do with such a superscalar, multiple issue, ideal processor? And this is how good I can. Those are benchmarks, typical benchmarks for integer and for floating point calculation. You know GCC, it's the compiler, but do you know the second one? It's not coffee. No? Never heard about. No. It's not related to that. It's no coffee, I said. You never did logic design in your lifetime? There is a program which is doing minimization of functions. Yeah, a long time ago. Okay. Now, that's not relevant, but the simulations were done on this ideal machine, and this is what we see. For integer, we can go up to 60 instructions per cycle in this machine. Then there is a limit, even though I have infinite resources. Then when I start allocating resources, if I get to 60, I should stop, because it will not make sense to put more, because I cannot get more. Not on those benchmarks, for sure. Now, that kind of evaluations, as I told you, are done based on benchmarks, and there is no mathematical calculation. Then if you don't choose the right benchmarks for your target, you are selling bananas to the client. And the client will not buy, for sure. Then what we see is that for integer is between 18 and 60 instructions per cycle can be processed in parallel, and for floating point we have even more parallelism. But this is ideal. Now the question is, if I now tweak the parameters, what will happen? And let us look on the impact of different factors. Then let us look on branch prediction. Then I can go from perfect prediction to no prediction at all, with the ingredients that I know, Turnman prediction, standard profiling, which is based on the compilation thing, it's static prediction. And this is what I got. Then, if I do no prediction at all, my instruction per cycle, even though I have infinite resources, is not brilliant. You see, on integers, I get 2 instructions per cycle with no prediction at all. While if I do perfect prediction on GCC, I can go to 35. Then the prediction has an impact on what I can achieve. And I see that there is good impact. Now, I also see that the impact is different than per benchmark. If I look at the last one, you can see that almost all of them, except no prediction at all, will give you the kind of limit of 45. Now, if you develop a machine which is application specific, you just care for 1 or 2 or 3 applications. If you develop a general purpose machine, you should try to evaluate on more benchmarks and create a figure of merit, which is an integration of the numbers that you get. Now, the same story here, but now it's different. I'm limiting the renaming registers, and I am trying to see what is happening if I have no limit on the renaming, no renaming, and registers between 32 to 200 something. And what you see is that somehow, for integer, there is no real impact. It's not very fundamental. I mean, if I look at Espresso, if I have 256 registers for renaming, I'm as good as unlimited. While for floating point, this is getting more important. Okay? And the simulation is done on a certain instance of the machine from other points of view. Then I'm just changing a parameter by considering the others in a certain space point. Now, because I have that many parameters, you may imagine that the design space is huge. And trying to find the optimal point in space is not simple. Okay, now I have to stop in the middle of this beautiful story with diagrams and colors, right? We'll continue next week.